Students, in today's video lecture, we are dealing with the second half part of the module 3, which is about the Fourier series representation of periodic signals, and which is mainly for continuous time signals. And in the previous lecture, I have shared some videos where we understood what is Fourier series representation for periodic signals and what are the equations which are related to this particular Fourier series representation. And today's lecture is about the properties of the continuous time Fourier series. And before we start discussing the properties of continuous time Fourier series, let us discuss the few points which we studied in the previous lecture, that is, the Fourier series representation for periodic signals. In the Fourier series, we have basically different types of transformation, that is transformation of one domain to another domain, mainly from time domain to frequency domain, time domain to Z domain, which is Z transform, and time domain to S domain, which is done by using a Laplace transform. So in many applications like signal processing and communication system, the widely used the transformation techniques are Fourier transform and Fourier series, as well as the Laplace transform in applications like the automation and control systems. So in the signal and system, we will be studying about the two important the transformations, which are Fourier series, and later we will be studying about the Fourier transform. So the Fourier series of any signal, which is mainly a periodic signal x of t, is given by x of t is equal to summation from minus infinity to infinity, because the signal is at the periodic, and capital X of k, which is multiplied by e raised to jk omega naught into t. And this capital X of k is known as the Fourier series coefficients for the periodic continuous time signal x of t. Since the signal is periodic, you will get the infinite number of coefficients, and that's why the limits for the summation is minus infinity to plus infinity. And these Fourier series coefficients can be calculated by the formula x of k is equal to 1 by t integration over t. Means since it is periodic, let us calculate the Fourier series coefficients over only one period, one fundamental period, that is only one cycle. So it is 1 divided by capital T, 1 divided by capital T, integration over one period, fundamental period capital T, x of t, and now this becomes e raised to minus jk w naught or omega naught into t dt, where x of t is the periodic signal has fundamental period capital T, and omega naught is the fundamental frequency, right? So it is fundamental angular frequency which is measured in radians per second. And as I said, this x of k is known as the Fourier series coefficients of x of k. And both this periodic signal x of t and its Fourier coefficient x of k, they are Fourier series pair. Means if you know any one signal x of t, you can easily calculate x of k. And if you know x of k, you can calculate x of t. That's why they are known as the Fourier series pairs, and they are denoted by like this x of t. And when you perform the Fourier series, you will get the Fourier series coefficients x of k. And where k is, it is a discrete Fourier case, the discrete frequency values. And whenever you calculate the set of the Fourier series coefficients for the given periodic signal x of t, you can plot its magnitude spectrum as well as phase spectrum just by taking the magnitude of each coefficient values. If it is real, then its absolute value will be real only. If it's complex value, then you have to take its magnitude, that is by calculating the square root of the square of real value plus the square of imaginary value. And in similar way, you can calculate the phase spectrum by calculating the angle of or phase of each coefficient in the side by simply taking tan inverse of imaginary value divided by real value, right? So in the coming lecture, we will be discussing in detail about how to calculate the Fourier series coefficients and how to plot magnitude spectrum as well as the space spectrum, right? So after that, coming to this lecture, that is about the properties of Fourier series. So like how we studied many properties in jet transforms, like linearity, it may be a linearity property, it could be a time shift property, it could be frequency shift, it could be convolution property, it could be a time scaling property, right? So like that, the similar kind of properties are also involved in the Fourier series concept also. And let us discuss the first property we have is the linearity. And we we come across this word linearity many times from the first lecture in the signal system. Linearity means any system is said to be a linear. It has to satisfy the condition like both homogeneity as well as the superposition, right? So what do you mean by this linearity means whenever the input is the weighted sum of the two input signals like x of t and y of t. So these are the two inputs x of t and y of t, and their weighted sum is given by x of t plus y of t, and that is equal to z of t, right? And now let us scale each individual input by some scalar values, that is a and b, where a and b are any constant value. So whenever there is a weighted sum of the scaled inputs a into x of t and b into y of t, the output is what? The response of the system for the individual inputs, right? The response of the individual inputs, and you have to take the weighted sum, right? So it is a into x of k, where x of k is the transformation of x of t, and y of k is the transformation of y of t, where here transformation is considered as what? The Fourier series transformation, right? So now let us see the statement, the linearity. If x of t, the Fourier series of x of t is capital X of k, and this x of k which is in frequency domain and x of t is time domain. So the Fourier series is used to transform time domain signal into frequency domain signal, and inverse Fourier series is used to transform the signal which is in frequency domain back to the time domain signal which is y of t, right? So the Fourier series of x of t is x of k, and Fourier series of y of t is y of k. Then let us take the weighted sum of these two input signals scaled by two different constants, a into x of t plus b into y of t, which is denoted by signal z of t, and its Fourier series is given by z of k is equal to a times the Fourier series of x of t is x of k plus b, which is a constant, and the Fourier series of y of t is y of k, right? Now we have to prove this property, right? So as we know that in the previous slide, we have seen the two formulas. One is for x of t and another is for the Fourier series coefficient x of k. And the Fourier series coefficient x of k is given by the formula 1 by t over integration over the fundamental period t x of t, which is multiplied by e raised to minus jk omega naught t into dt, right? And similarly, we can write the same for the second input signal y of t, and its Fourier transform y of k is given by the same equation, only the input is changed here. In place of x of t, you should write y of t, right? And the third signal which we have is, which is the weighted sum of the two signal, which is denoted by z of t. And if you take the Fourier series coefficient of this z of t, that is, we'll get z of k, which is 1 by t integration over t z of t e raised to minus j k w of t into dt. And this equation, we know that what is this z of t, and this z of t is weighted sum of the two input signals x of t and y of t, and they are multiplied by a and b respectively. So now let me substitute that z of t is here, and which is multiplied by e raised to minus j k w naught omega naught t into dt. And now let me simplify this one by opening a square bracket. So we'll get 1 by t as it is. And here a, which is scalar value, it is constant. Let me take outside the integration, and integration x of t, and this x of t is multiplied by this common exponential signal e raised to minus j k w omega naught of t into dt, plus again this b is constant, and this 1 by t integration y of t into e raised to minus j k omega naught t into dt, right? And just look at here, 1 by t, except this a, that is constant, this 1 by t integration t x of t into e raised to minus j k, this term is nothing but is what? X of k. So I will write a constant multiplied by this whole expression is nothing but x of k plus b constant, and this 1 by t integration of y of t, which is multiplied by this term, is considered as what? Y of k. Therefore the z of k, which is a into x of t plus b into y of t, its Fourier series is given by a into x of k plus b into y of k. And next property we have is time shift, right? So if x of t, its Fourier transform series is given by x of k, then whenever we add some time shift, whenever the signal is shifted by some unit, say t naught, then its Fourier series is given by e raised to minus j k omega naught t into x of k, right? So whenever you introduce some shift in the time domain signal x of t, the Fourier series, the output x of t, x of k is multiplied by the exponential signal with the same unit which you introduced in the time signal. That is, here you can observe e raised to minus j k w naught into t naught. This should be t naught, right? So here some mistake is happened. So this should be t naught. So again, take basic definition: x of k is equal to 1 by 2 x of t into e raised to minus j k w naught of t into dt, and we'll take the output w of k is equal to 1 by t w of t e raised to minus j k omega naught t into dt. So let us substitute this w of t, and this w of t is time shifted version of the input signal x of t. So now let me substitute wt as this x of t minus t naught and multiplied by e raised to minus j k omega naught t into dt, right? So now let us substitute here x of t minus t naught is there. So now let us make an substitution by t minus t naught is equal to m, right? So when t minus t naught is equal to m, then the differentiation dt becomes what? The dt is equal to what? Dm, because it is differentiation of t with respect to m, right? So it is dt is equal to d. So wk is equal to 1 by t integration, and t minus t naught is equal to m. So x of t minus t naught will be x of m e raised to minus j k omega naught. Now when t minus t naught is equal to m, what is for t? So t becomes, just you shift this minus t naught right side, this becomes m plus t naught. So in place of t, I am writing m plus t naught, and here this dt becomes what? Dm. So when you differentiate t with respect to m, right? So dm. So now let us simplify this exponential term e raised to minus jk omega naught into m, that is the first term, into e raised to minus jk omega naught into t naught, and here it is dm, right? Since in the input we have the argument m, so signal is a function of m, and here the differentiation is with respect to a variable m, parameter m, and here in the exponential term also we have m, but this term, if you see, here we have p naught, and this is the constant. You can treat this exponential term as constant because it is not a function of m, right? So that's why this constant will take outside the integration, and it is 1 by the integration x of m e raised to minus jk omega naught m into dm, right? So except this exponential term, look at this term 1 by the integration x of, is it the Fourier series representation of x of n? Yes, it is denoted by x of a. Only in place of x of t, we have x of n. So you can write x of k, right? So finally, w of k is equal to e raised to minus j k w naught into t naught x of k, right? You may uh, mm, call this one as w naught or omega naught, both are correct, right? So this is what the expected, the proof wk is equal to e raised to minus j k w naught into x of k. Move on to the next property, which is frequency shift, right? So when you will get shift in the frequency means obviously it is capital X, that is uh, x of k. So it is not a x of s, it is x of k. So if the Fourier series of x of t is x of k, then whenever you multiply the input signal x of t by some exponential signal e raised to j k naught omega naught into t, then only you will get corresponding shift in the frequency domain signal, that is x of, now x of k is now shifted by what? K naught. So x of k minus k naught. Whenever you want to make some shift in the output, you have to multiply the input signal by what? Some exponential signal with same constant, that is a k naught. So now let us prove this one. X of k is equal to 1 by t integration x of t e raised to minus jk omega naught t into dt, right? So what is the output? Gk is there. So let me write the equation for gk in terms of what? The input gt. So gk is equal to, again, integration g of t, the rest of things is same, 1 by t. Now let us substitute g of t. So when I multiply x of t, this one, by this exponent signal, and whole thing is considered as g of t, and this g of t is e raised to j k naught omega naught t into x of t. So that I have written here, and after that it has to be multiplied by this e raised, followed by e raised to minus jk w naught into t. So I will write x of t as it is, and here we got the two exponential signals with the different polarity, right? So one is plus and another one is minus. So let me take from both these exponential terms some common. E raised to j k minus k naught is, right? E raised to j omega naught is common, and here you can write k minus k naught, right? So by comparing this equation number 1 and equation number 2, RHS of equation number 1 and equation number 2, you can write g of k is equal to x of k minus k naught. And the last property is here the scaling, time scaling. So you have to scale the signal x of t. So z of t, if x of t Fourier series is x of k, then if you scale the signal, time scaling, that is x of a into t, which is considered as z of t, I will denote it by z of t, then its Fourier series equal to what? This is same as of x of t, right? Even if you scale the signal by time, its Fourier series remains same as that of the original input x of k, and this a should be any positive quantity, right? So now let me prove this one. X of k is equal to, this is a basic definition, and the output z of k in terms of z of t, and where z of t is what? X of a of t, x of a into t, right? So you have to remember two things. Whenever you scale the input signal, after scaling the input signal, the fundamental period t becomes the t divided by a. A is what? The scaling value. And the fundamental frequency omega naught becomes what? A into omega naught. So these are the two important points you have to remember. Whenever you scale the signal by any value, the fundamental period of the scaled input signal t becomes t by a, and the frequency becomes a into omega naught. Right? So now let me use all these things here. Z of k is equal to 1 divided by t divided, because this t becomes what now? T divided by a, and this is also t divided by x of a into t, because z of t is equal to x of a into t, e raised to minus j k into this w naught becomes what? A into w naught now into dt. So here let me substitute a into t as m, and differentiate t with respect to m, you will get dt is equal to dm by a. Substitute. So if I take this denominator to numerator, this becomes a by t. A of t means m. Substitute 1 by a into dm, that is dt. This a and this a get cancelled, and you will get finally 1 by t integration x of m e raised to minus j k omega naught into m. And this is nothing but what again? X of k. Right? So these are the few properties we discussed in the today's lecture. A few more properties are remaining. They are discussed in the next lecture.